So welcome back. So we just finished off doing this parallel axis theorem where you have the moment of inertia about the centre of mass, and you want to find the moment of inertia about an axis that's parallel to the one you have through the centre of mass. And you know the mass of the object, and you know the displacement of the objects, of the two axes. So. Rotational kinetic energy. Okay, so we know that linearly kinetic energy equals a half mv squared, so we know that rotationally kinetic energy equals 1/2 I omega squared. Now, these are two independent energies. So it takes energy, or it depends on semantics, it takes energy to spin. If you want something to spin, you've got to put energy in to make it spin. If, on the other hand, it's just sliding, you don't need to put that energy in. So I'm going to draw a bit and then I'm going to do a little problem. So if I have a ramp which is frictionless, say ice, and I put a ball on there, and the ball does not spin, if there's no friction, there's no reason why the ball should spin, then that ball will convert that amount of gravitational potential energy into KE linear or translational or something like that. KE linear or translational. If I have the same situation and I have the same UG and the same ball, but now this thing, there's some friction involved that doesn't stop the thing from translating, but means it has to roll. Then I not only have when it gets to the bottom, that becomes my UKE linear plus my KE rotational. And that's the problems we're going to head towards. So if I have so much energy and I'm only putting it into translation, I will get faster translation at the bottom. Then I have the same amount of energy and I not only put it into translation but also inevitably into spinning, because it costs energy to spin. Or otherwise, if you like, you can store energy by virtue of the spinning. And that's what a flywheel does when you think about it. The reason why you have a flywheel on your car engine is because you only get power out of one of the 4 strokes. For the other 3 strokes in the car engine, you're taking energy from the engine and putting it back in to keep the system working. You're paying to open the valves and pull down the piston and draw the fuel in, and then you're paying to compress the gas. And then suddenly when you ignite the gas, you get energy back out. So you need a storage device to take the energy from the power stroke and be able to use it in the other strokes. And that's what your flywheel does. It smooths out the workings of your engine. And that's rotational kinetic energy. That's the storage of energy by rotation. So you can think of it as a cost, and you can think of it as a resource. So, and we like asking questions about this. So let's have a look at this. So what we have here is we have a question. This question says, let's have a look. A system consists of a body having a moment of inertia of 5 kilograms meter squared, which rotates at 3 radians per second about its turning axis. What is the rotational kinetic energy of the system? So here's the body. Here's my rotational axis. It's spinning. What we say is, I want to find the rotational kinetic energy. KE rot is equal to 1/2 I omega squared, which equals 1/2. Do we have a I? Yes. 5 times 3 squared. KE rot is equal to 1/2 times 5 times 9, which equals 5 nines are 45, and 1/2 of 45 is 22.5 joules. Nah, so that looks straightforward. But what can I do to make it more interesting? Well, maybe I could give you the tangential velocity. And then you'd have to convert to get your angular velocity. Maybe I give you the mass and the radius and tell you it's a solid cylinder and have you work out your moment of inertia. I can dress it up a whole bunch of ways. So watch out for that. There's this cartoon I saw, and it said, basically students complaining about the questions that my instructor does in class are really easy. The questions that my instructor gives for homework are much harder. The questions that my instructor gives for a test are impossible. I wish I was the instructor. It's kind of like, I get the easy questions, you get the harder questions. And it's very true. There's a logic behind that. Is I want to get the principle across, but don't get lulled into this idea of, well, that looked easy. That's a piece of cake. I can dress things up, and that's putting on your game face. And that's where the homework's important. I try to go to the next level in the homework, and then the previous exams are most important. My feeling is if you go straight to the previous exams, you won't have, it's like not going to the gym. It's like, I got a race on Saturday. I'm just going to run a couple of races the day before, and I'll be in good shape. But you never go to the gym for 3 months or whatever. Then you're not going to be very good. But if you go to the gym and get really fit, and then you do a couple of races beforehand, and then you do the race, you'll be really good. If you just go to the gym and then you do the race, you'll be rusty on technique and all that kind of stuff. So it takes it all. So really do, the resources are there for you to use. I don't collect them because there are some people who don't need all that homework. There's some people who don't need what, I've prescribed. I don't want it to be that you don't have stuff. That's what frustrates me. When you get to the upper division courses, the textbooks tend to have relatively few homework questions at the back of the chapters. That's the big distinction between lower division courses and upper division courses. The upper division courses, they tend to ask fewer questions at the back, which always frustrated me because it means there's less practice at the back. So, and I remember running out of questions. When I was struggling, I was running. I'd try the first question. I wouldn't be able to get it. I'd go to the back of the book. I'd look at the answer. Oh, man, I got that wrong. Let's see what I did wrong. Oh, I get it now. Go to the second question. Didn't get it right. Oh, what did I do wrong? And I'm learning every time, but there was never a time when I got the question and I did it right. And it was like, I don't know if I know this stuff, I don't want that to be the case. I can't do it. I can't guarantee it, but that's my aim. My aim is to give you more questions rather than less. But you should sample. You should do at least some of the homeworks. If you're finding it a piece of cake, then you can move on. But I do think it's like doing reps. I do think it is like weightlifters don't do 100 reps because they need to. They do 100 reps because they want to stay really, really fit. So it's kind of like that. Anyway, so always look for how I can dress things up. And remember, I can change the numerical thing. I can make it into a two-stage problem. I could ask for you to plot me a graph of the KE rotation versus angular velocity and not call it omega, in which case you have to know that's omega, in which case that goes like that. I can ask you to do me a ratio problem. There's a whole bunch of things I can do with it. It'd be nice if all this worked out. So K rotational, the K total, that's K total, is equal to a half mv squared. That is K translational plus a half I omega squared. And that's K rotational. So what we've got here is we have a system, a circular wheel rolling along a surface without slipping. So its center of mass does translate along the bench, and it is a translational kinetic energy. But there is also the rotation of the mass around its center of mass, and so there's a rotational bit as well. I could describe this same behavior by assuming that all the mass simply rotates about an axis where the circle is touching the surface. And then when I'm down here, I have what looks like the same diagram, although, you know, let's have a look. If this was touching point A and that was touching point B, this would be touching point B. So the actual touching point just does change, but the actual mechanism is the same. It's just a rotational mechanism. And for that, my I total would equal half I omega squared. But these I1 is not the same as I2. You can see that. Here's my axis, so this is going to be a very big I value. And omega 1 is not the same as omega 2. So I prefer to do them this way. Okay? And here's the classic example. So a cylinder of 4 kilograms mass and 3 meters radius rolls along a surface. What translational kinetic energy, with a translational kinetic energy at 6 meters per second, what's its total kinetic energy? So we say K total is equal to K trans plus K rotational. So K total is equal to translational kinetic energy is going to be a half mv squared plus 1/2 I omega squared. And what do I know? I know the mass is equal to 4 kilograms. I know that the radius r is equal to 3 meters. And I know my v is equal to 6 meters per second. So I can do the first bit. Oh yeah. K total is equal to 1/2 times 4 times 6 squared. I got that bit. But now for this next bit, oh man, I need to figure out what's going on. I didn't use the term solid cylinder here, but I should have done. So for a solid cylinder, it's a half mr squared. And then for my angular, so let's put this down. I solid cylinder equals 1/2 mr squared. And then my, let's have a look. And then my omega is equal to my v tangential over my radius. Remember that angular? So this is going to be v squared over r squared. Oh, call it the same letters. V squared over r squared. So then I say, well, my K total is equal to 1/2 times 4 times 6 squared plus, let's have a look, 1/2 times 1/2 is 1/4. The mass stays in. Those r's cancel. Oh, that's interesting. Well, dimensionally it should be the same, shouldn't it? Because we're adding them. So we should end up with mass times velocity squared. So this is 1/2 times 4 times 6 squared plus 1/4 times 4 times 6 squared. So, oh, I cheated, but I'll come back to it. K total is equal to 2 times 36 is 72 plus 1/4. 1 times 36 is 36, which equals 108. And it's going to be joules. So we see it. We basically said it's translational kinetic energy and rotational kinetic energy, and it was half mv squared, and by analogy half I omega squared. I substituted in what I knew, and then I had to scratch my head. And now I'm drawing on a whole bunch of equations that might not be so familiar because we just did them, but you've got to get familiar as quickly as possible. So my moment of inertia equals, for a solid cylinder, is 1/2 mr squared, and my Angular velocity is v tangential over r. Got a square top and bottom. I cheated a little bit because this is a tran and this is a tan. Tange. What's the difference? There's my v tran. Here's my v tange. V tangential. You know, this omega is equal to v tangential over r is not necessarily the same as v translational over r. They're different places on my diagram, yeah? So there's a relationship between these two, and it turns out that it's a one-to-one relationship. And I got to be honest with you, when I was told that, I accepted it, but I was never comfortable with it. And then finally I got some kitchen towel, and I put my finger on that end, and I rolled it, and I said, oh, that went by 1, 2, 3, 4, 5 sheets per second. And then I put my kitchen towel like that, and I put my rod or my finger, whatever, I held that in place, and I pulled my finger in that direction and went the same thing, and I said, I unrolled 1, 2, 3, 4, 5 sheets per second. And that convinced me that my translational velocity, 5 sheets per second, was the same as my tangential velocity. I took off 5 sheets per second and did that a few times. I convinced myself that my translational velocity is the same as my tangential velocity. Because it's symmetrical. From the towel's point of view, the towel's going in that direction. From the canvas point of view, the towel's going in that direction. So, do I pull the towel or do I pull the roll of towels? That's the difference, isn't it? In the top one, I'm pulling the roll of towels to the side. In the bottom one, I'm pulling the towels to the left. Roll of towels going to the right is like the towels going to the left. So it's the same thing. So V tangential is the same as V translational. So I can just put the same number down for both. This is a classic. 4 kilogram hollow hoop that has a radius of 2 meters is placed at the top of a 30 meter tall ramp. It rolls to the bottom of the ramp without slipping. meters. 2 meters. 4 kilogram. What is the speed? V. Speed equals V, which equals V trans. I'm just not worried about its sign or its direction. Yeah, the speed is the velocity without the direction. So the first thing I'd recognize is this is conservation of energy. So there is frictional force to cause the rotation, but it's not sliding friction, it's static friction. Yeah, it's just like rolling along the surface. So there's no energy lost. Remember what we said about the tires? There's no energy loss to friction, energy loss to heat when you got static friction. So because you're rolling, it's static friction, because you lay the towel down and lift it off, and you lay the towel down and lift it off. It's not like you're sliding the towel, sliding the cylinder across the surface. That's when you squeal your tires. And there's a lot of energy lost to heat. But we're not screeching our roll along the surface. It's just rolling. So it's a static friction case, and there's no energy lost through friction to heat. So it's conservation of energy. So the mechanical energy, initial, equals your mechanical energy final. And we're going to say, well, we have M times G times H initial. That's our PE initial. Plus 0, that's our KE. No, I'm not going to do that because it's going to get too complicated. That's all we have initially. It's stationary at the top. It's not spinning. It's just got height. And that equals our, well, a half mv squared. That's going to be our KE trans final plus 1/2 I omega squared. And that is our KE rot final. Down here we have translational kinetic energy and we have rotational kinetic energy. That's omega. So mgh is equal to 1/2 mv squared plus, now remember that for the hollow hoop I, hh is equal to mr squared. It's a hollow hoop. So I've got to say, oh, that's going to be a half times mr squared. And then again we have this thing about V tangential is equal to omega squared, omega over, omega is equal to V tangential over R. So we're going to say, oh, this is going to be V squared over R squared. We should put down here V tang, V tang is equal to V tran, just so we can justify having the same V in both cases. So mgh is equal to 1/2 mv squared plus a half mv squared, which equals mv squared. Okay. So v squared is equal to mgh over m, which equals gh. So v is equal to the square root of gh, which equals the square root of 300, which equals, so that's going to be second square root 300. That's going to equal 17.3 meters per second. That's how fast it's going to be going when it gets to the bottom. So we visualized, we recognized that there was conservation of energy. We recognized at the top there was only mechanical energy, there was no rotation, there was no translation, there were no springs, so it was just potential energy, mgh. And then we realized at the bottom there was a combination of, there was no longer any potential energy because we're at the bottom, but there was a half mv squared because of translational kinetic energy, and there was a half I omega squared because of rotational kinetic energy. As before, we had to substitute in for the moment of inertia, so our three equations become very important. The moment of inertia for a solid cylinder, the moment of inertia for a hollow hoop, or the moment of inertia for a solid sphere. We've got to know those. And then we also had to recognize the fact that, you know, using our angular R system, omega R is equal to V tangential, so omega is equal to V tangential over R. So we had to substitute in for this omega squared. we had to recognize the fact that our V tangential and our V translational are actually the same value. So we can just call it V. And then the rest is math. Classic question. I'll tell you, this is a question that is pushing you on where I can push you on thinking in sentences. All I have to do is not tell you the mass. So you can't work out that potential energy because you don't have the mass. You can't work out the kinetic energy of translation because you don't have the mass. And you can't work out your kinetic energy of rotation because you don't have the mass. And I'll tell you, if I do that, there'll be a couple of people in the test will say, I can't do this question, you forgot to give us mass. And I will say, you don't need mass. Or I will say, I'll deal with it later, just do the best you can. Because what I'm testing is, do you think in sentences, and do you recognize, oh look, mass cancels out. So you don't need the mass. So watch out. That's a next stage of subtlety, but it's something that can be done. You know, it's kind of like trying to test the people at that next level, where they recognize that you don't need every last thing for every last factor in every last equation if you're thinking equations. But if you're saying a half mv squared, what's that? I don't have a number. Oh, you know, a half I omega squared, I don't know that. Oh, mgh, I don't know that. If you're not thinking in sentences, if you're not putting down equations with equal signs, then you're going to pay a price. And frankly, you should pay a price, because you're going to be limited in your utility as an engineer as you go forward. You know, it's not just like, you know, the slow people at the back of the class after thinking equations. We all are better when we think in equations. So, you know, you'll be better if you think in equations. And people will push you on it all the time, more and more. So if you're not used to writing equations down, see it as a real liability. It's not a style, it's a liability. So see it as a real liability. It's not the end of the world. It doesn't make you a bad person. But it means you're not punching at your full potential, because you got this, you know. I met, well, I'll tell you, I met a world-class boxer a couple of weeks ago. He was at some party, and this guy's there, and somebody I know knows him. And he's not a heavyweight. He's a you know, my size, but incredibly fit. I mean, the guy's, and he's retired now, so he's more my age. But I said to him, what do you do? I said, well, I train people in boxing. And I said, oh yeah. I said, did you box yourself? What a stupid question. Did you box yourself? And he goes, well, yeah, I was the world champion, you know, flyweight or heavyweight or lightweight, whatever it is. Boxer from so-and-so to so-and-so. And I said, oh, wow. He said, oh, yeah. He goes, I was always interested in it. He said, and I figured out, guy was clearly bright. And he said, I said, is it true that in terms of athletes, it's all in your head? And he said, well, he goes, you got to be a thinking boxer. He said, I lost my first 7 fights when I was an amateur. I said, you didn't give up? He said, no. He goes, I was learning from them. I deliberately challenged people who were much better than me to kind of find out what I was doing wrong and what they were doing right. And then he went for some ridiculous length of time undefeated. And he said, I said, did you watch videos of the people before? And he goes, yeah, you do that. He goes, but he said, you're looking for, you know, the tendency to drop your fist when you punch. And he goes, and if you watch, you'll see it. And once you see it, that's what you're looking for. You're looking for the way in. Has a tendency to do that. I saw him do it once. I saw it do him twice. He's out. Because the next time I'm ready and I'm waiting for it. You've got to withstand the pain while he's knocking on you. You're kind of letting him knock on you to look for his weakness. and then you go for it. And very thoughtful, very deliberate person who was willing to take a few knocks early on to get better, but was constantly trying to get better. And I must gotta confess, you know, I said to him that I thought sports, I never was a sporty person myself, but I thought that sports had this value in that it seems to teach people that you can get better by practice. Same with music. I think music teaches you can get better with practice. If you pick up a guitar, it's awful. But a year later, you're doing really well. And so not doing this now does not make you a bad person. It just means to say you're dropping your left hand when you hit with your right. So stop it, you know? Write in equations, and you'll lose fewer points because of it. You'll be a stronger engineer because of it. So just do that. Cool. So there we are. There's the end of it. Let's pause it there.